Hey all, welcome to part 4 of the strong nuclear force as a gauge theory. Today we're going to be deriving the field strength tensor of quantum chromodynamics. Now today's video is going to be very mathematical. We're going to have a lot of equations, and that's just how it is. So just a heads up. But as always, those equations are in service of the beautiful idea that the strong nuclear force blossoms from local SU3 symmetry. So where we left off in part 3, we derived a gauge field which gave our Lagrangian local SU3 symmetry. But then we thought, hey, wait a minute, our Lagrangian doesn't give G mu a life of its own. And that's a problem because if we're saying that our gauge field exists and is real, then it should have some life of its own. There should be energy associated with the way that the gauge field itself is scrunchy or floppy or something, you know what I mean? Because it wouldn't really make sense for G mu only to exist insofar as it interacts with psi. And so now the question becomes, how can we bring G mu to life all the way and let it manifest in its full glory? So if we go back to the golden rule, the magic bean, that the strong force blossoms from local SU3 symmetry, then the answer is that the most zen way to give G mu a life of its own is to let it contain energy in whatever way it can, without violating the local SU3 symmetry that justifies its existence. So we brought the gauge field G mu into existence in order to give our Lagrangian local SU3 symmetry. And therefore, whatever life we give to G mu, whatever field we come up with that's going to encode the energy purely contained within G mu, that entity or that field can't itself violate local SU3 symmetry, because then our model would be logically incoherent. Okay, so we have to find a field that we may as well call F, which encodes the energy contained purely in the gauge field G mu. Now, as we talked about in the last video, this is actually going to be the field strength tensor F mu nu. But I don't even want to call it F mu nu yet. I want to think about this from a really blank slate perspective, where we're open-minded to the idea that F could be all kinds of different fields, potentially. Maybe it's a 4-vector field, maybe it's some kind of super complicated field, who knows? We don't yet know that it's going to be a rank 2 tensor. But that's something that we'll want to prove when we think of all the possible things F might be, we can imagine it being. What is the only thing that it's actually allowed to be in accordance with local SU3 symmetry? And we'll find that that is our field strength tensor F mu nu, but with a non-Abelian twist. Okay, now the next guiding principle that we're going to use is that if F is going to somehow correspond to or encode real observable energy, then from one gauge to another, it should undergo the adjoint transformation. That is, F in the new gauge, F prime, should be F in a UU dagger sandwich. Because remember, our gauge field G mu goes into a UU dagger sandwich under a global SU3 transformation. And as we saw in the last video, that UU dagger sandwich is going to appropriately readjust the gauge field in color space. And for the same reasons that we saw in the last video, that G mu has to undergo that adjoint transformation, it also turns out that our field strength tensor F should also undergo the same transformation. And the way to look at that is, as we hop from one gauge to another, F is going to reorient itself properly in color space, which is totally appropriate. But other than that, it's not going to transform. And so it's not going to be messed up. Now, if you think about F as some field that is based on G mu, that pertains to G mu or its derivatives or something, then the fact that as we hop from one gauge to another, it's simply going to undergo this adjoint transformation tells us that this field F has some kind of real identity to it, regardless of our gauge choice. Okay, so to give our gauge field G mu a life of its own, we have to find some kind of field F that transforms in the UU dagger sandwich as we hop from one gauge to another, but otherwise doesn't transform. Now here, I want to use a metaphor where we're going to think about the gauge transformation rule for G mu as a lock. Now what I mean by that is you hop from one gauge to another, and the gauge transformation rule tells us exactly how our gauge field G mu has to transform. And then this field that we're looking for, F, the field strength tensor, but for now we just know it's some kind of field F that has to have an identity of its own, has to be largely unaffected by that transformation, except for the appropriate reorientation in color space. So what I mean when I say that the gauge transformation rule is kind of a lock is that only a specific definition of F is going to be able to preserve its identity in the appropriate way under any arbitrary gauge transformation. And so in that sense, the specific definition of F that we're looking for is kind of like a key, and you know you found the right key when you hop from one gauge to another, and the key simply turns with a UU dagger sandwich, but otherwise isn't like destroyed or warped or twisted or scaling up and scaling down. Okay, so this metaphor is not perfect, but I think it kind of works. I was going to use another needle in the haystack analogy, but we already used that, so we'll just go with this for now. But it is very much also a needle in a haystack in that of all the possible definitions of F that we can imagine, of all different fields that we can define and make up, only a very specific definition is actually going to work here. Okay, now if we put on our mathematician hats, we can think of this as a nice mathematical problem. Given our gauge transformation rule, what field F can we define that depends on g mu and that transforms in the appropriate way under a gauge transformation? Well, finding a field F that transforms neatly in the appropriate way is actually easier said than done. Because if you think up some random expression for F in terms of g mu, or its derivatives, or second order, third order, any order of derivatives, it's almost surely going to fail. Because what happens is the derivative term in our gauge transformation rule, that is that partial mu of u, is so wild and so arbitrary when you think about all possible SU3 transformations, that surely it's going to transform F in a messier way than simply reorienting it in color space. Because, for example, let's say F is simply going to be the derivative of g mu. So let's say F mu equals partial mu g mu, right? Well, then you hop into a new gauge, and g mu prime is modified in accordance with the gauge transformation rule, but that derivative term, partial mu of u, depends on our SU3 matrix field u of x. And so the derivatives in our matrix transformation field are going to end up changing the value of g mu at different points in space and time, and so it's going to end up changing the magnitude of the derivative of g mu at different points in space and time. And you know what? In fact, the most straightforward example is what if we just said F mu is proportional to g mu, right? So what if we wanted to say that the way that we're going to give our gauge field a life of its own is simply that there's some field that's directly proportional to the amount of the gauge field that we have? Well, that doesn't work, and for the same reason, because that derivative term, partial mu of u, is going to break up the proportionality between F mu and g mu when you hop from one gauge to another. Because when you go from one gauge to another, and g mu becomes g mu prime, that derivative term is going to add or subtract to the magnitude of g mu. And so if this field that we're trying to construct is F mu, then that's also going to be increasing and decreasing, and that's more than just a rotation in color space, and so that's not allowed. That's not the field that we're looking for. And you can apply the exact same reasoning to any F mu nu that's proportional to a derivative of some order along some space-time dimension of some component of our gauge field raised to some power. So you can think of this kind of generalized form of like derivatives of the gauge field, and in all of those cases, that derivative term in our gauge transformation rule, by changing the magnitude of our gauge field, is going to mess with the magnitude of all of those different ways of writing expressions based on g mu. And so you play around with this for a while, and you realize that basically any field that you write as some function of g mu and or its derivatives is going to be totally messed up by an arbitrary local SU3 transformation because of the way g mu transforms. And if you think back to the electromagnetism video, you realize that this is, in essence, exactly the same problem we had when we were trying to give our photon field a life of its own. See, because when it comes to electromagnetism, we brought in the photon field to clean up the mess created by a local U1 transformation. And then we were like, okay, what are all the ways that A mu can contain energy without violating local U1 symmetry? And we found that there was a very particular loophole, F mu nu equals partial mu A nu minus partial nu A mu, right, the 6 ways. And in this expression, each derivative is going to change under a local U1 transformation, but it's going to change in an equal and opposite way. And so in our lock and key analogy, this particular expression, these derivatives set against each other, are the specific key that's able to open the lock. And this isn't just some abstract mathematical thing, because we thought about, okay, what is this expression anyway? And we realized, as we talked about at the end of the last video, that we have 4 choices for the space-time indices mu and nu. So we have 16 choices total for mu nu, and then 4 of those cancel to 0 because when mu equals nu, you end up getting a thing that just cancels itself out. And then the remaining 12 terms are redundant because of the anti-symmetry, right? F mu nu equals negative F nu mu. And so those are what we've been calling the 6 ways. And those 6 ways are not just math, they're physics, and they're actually physics that everyone knows and loves because the 3 ways that include space and time, those are the components of the electric field. And the 3 ways that are based on space and space, those are the components of the magnetic field. So then we see that the electric field and the magnetic field are nothing more than the 6 ways. So what a beautiful story that is for electromagnetism. And we know electromagnetism is a gauge theory, and the strong force is allegedly a gauge theory, and so maybe we can just do the same thing here. What do you think? Given that this 6 ways approach was a remarkable success for electromagnetism, can we just do the same thing here? Define F mu nu equals partial mu g nu minus partial nu g mu? Is that going to work? Is that going to lead us to a triumphant success? No. If we try to use the 6 ways, we find that our attempt will fail. But that doesn't mean we shouldn't try. Because sometimes failure happens. But if you carefully examine the shape of your failure, therein lies the key to success. And that's not just physics, that's wisdom. That's life. After all, are you not the product of 4 billion years of trial and error? On this planet? In this cosmos? Made of stardust? Billions of light years across, billions of years old, expanding into a destiny unknown? So can't we claim this moment, right here, right now? This small little pocket of space-time, can't we devote this to trying the 6 ways and seeing what happens? All right, let's see what happens. Okay, using failure as a gateway to success, let's try the 6 ways. So we're going to assume that F mu nu is partial mu g nu minus partial nu g mu. Now let's remember the rules of the game. So when we hop from one gauge to another, our gauge field g mu is going to have to transform into g mu prime, which we get by putting g mu in a u dagger sandwich to reorient it properly with regards to color space. And then we also add on this derivative term, which cleans up the scrunchy and the floppy mess that we're making with our local SU3 transformation. Now we're hoping that our field strength tensor is going to basically not transform from one gauge to another, except for being put in the u dagger sandwich that is going to properly reorient it in color space, but otherwise leave it completely unaffected. So to try the 6 ways, the question simply becomes, is it true that the 6 ways in the new gauge, partial mu g nu prime minus partial nu g mu prime, is equal to the 6 ways in the old gauge inside a u dagger sandwich? See, because all we've done there is we've substituted in F mu nu prime and F mu nu for our proposed definition of F mu nu as the 6 ways. All right, well, let's go ahead and evaluate this equation and see if it's true. So we suppose that F mu nu prime is equal to the 6 ways in the new gauge. And we can go ahead and expand that out by evaluating those G primes. The G primes are the gauge field in the new gauge, but we know what that has to be because we have the gauge transformation rule for G. And so we can just go ahead and put that in here. So now we have an expression involving G in the original gauge, and all we have to do is see if we can reassemble it into the purple equation shown above. So before we can reassemble something, we have to break it down into its pieces and see what building blocks we have to work with. So to that end, let's go ahead and evaluate these derivatives using the product rule. All right, so if you want to take the derivative of the product of 3 matrices, say A, B, C, then that's going to be the derivative of A times BC, plus A times the derivative of B times C, plus AB times the derivative of C. And if you just had two matrices, then the derivative of AB is going to be the derivative of A times B plus A times the derivative of B. Well, now, first of all, let's go ahead and evaluate that three-matrix expression U G nu U dagger. Taking the derivative, partial mu, of that term gives us the derivative of U times G nu times U dagger plus U times the derivative of G mu times U dagger plus U times G nu times the derivative of U dagger. Likewise, if we apply the product rule to the derivative term, which involves two matrices, we end up with the derivative of U times U dagger plus the derivative of U times the derivative of U dagger. Now here we have to be mindful that our derivatives have different spacetime indices, so we don't want to mix up our mu's and our nu's. All right, so now we've unpacked that orange term into its constituent building blocks, and let's go ahead and do the same thing for the purple term, which is the same as the orange term, but with the mu's and the nu's switched around, and with a minus sign. So we'll just go ahead and write that out like so. All right, well, we've got quite a mess here. A lot of U's and U daggers and G and mu's and nu's. So the question comes up, can we cancel anything out here? Well, in general, because of the non-commuting nature of these matrices, we can't cancel out most of these terms, even though it kind of seems like they should want to cancel out. So there's really not much we can do. But there is one of these terms that involves a second derivative of U, and the only difference there is whether you take partial mu, partial nu, or partial nu, partial mu. But those will actually be the same, because that doesn't matter, because one of the implicit assumptions about a local SU3 transformation is that our matrix field is going to be smooth and continuous and differentiable, so the order that you take a second derivative isn't going to matter. So those terms actually will cancel out. So at least there's that, okay? At least something cancels, so that's nice. All right, but we still have a decent mess left over. So what can we make of this? Well, actually, you know what? Go ahead and look at these purple terms here. We've got a couple of derivatives of the gauge field, each inside of a U dagger sandwich, and you realize you can pull those together, and what you end up getting is F mu nu in a U dagger sandwich. Because think about it, you got partial mu G nu minus partial mu G mu, both inside of the sandwich, and so that's none other than the 6 ways in the sandwich. So that is U F mu nu U dagger. So that's really cool because that's what we're hoping the entire expression is going to equal. And now all we have to hope for is that all the rest of this stuff is going to cancel out somehow. So let's see if it actually does. Well, consider these blue terms. If you stare at this for a while, you realize you can factor this into some expression that's all inside of a U dagger sandwich, shown here. And so I'll draw the arrows showing which term goes where. And there's really nothing too special about the way I've written it here. The basic idea is just how can we bring together these blue terms in a way that kind of, I don't know, makes it look nice or something. And so that's all there is to it. It doesn't, there's nothing special about the way we've written it here. What are we to make of this blue term? Well, looking at it, unfortunately nothing really cancels out. And you can think that if only these matrices commuted, then maybe you could switch around the derivatives and the g's, and maybe you can get some kind of thing that might cancel out, but no, unfortunately it doesn't cancel out for SU3. All right, and we can't forget about these green terms. We still have to contend with those too. Well, there's not much we can do there. I guess we can pull out a common factor of I over g and write it like so. But again, these terms don't really cancel out. Even though it looks like something that totally would want to cancel out, if only U were like a matrix in an abelian group, but nope. All right, so what can we conclude from this? Well, we did find this term that we were looking for, U F mu nu U dagger, but we also got all this yellow stuff too, and that just doesn't cancel out to 0 because of the non-commuting nature of an SU3 matrix, and the fact that G mu is in SU3, and so those don't commute either. Well, interestingly, all this yellow stuff does cancel out if we were dealing with electromagnetism, where U equals e to the I theta is a U1 element, and our gauge field is just the electromagnetic 4 potential whose components are real valued. In other words, they live in the Lie algebra of U1, because those things all commute. And so the yellow term is there implicitly, but it always equals 0 when you're dealing with electromagnetism. And that's another example of how non-Abelian gauge theory is to a rectangle as Abelian gauge theory is to a square. A square is a rectangle, but a rectangle isn't a square. And here, this yellow term that we're encountering, this has to do with the extension of the rectangle that we don't normally have to deal with if we're used to dealing with squares. Anyway, all that's to say, remember the lock analogy, where we're thinking about the gauge transformation rule as a kind of lock that we're trying to pick? Well, if we were dealing with electromagnetism and we try the 6 ways, and we don't end up with this yellow term because everything cancels out, then the lock would pop open by now, and we'd be done. And that's why the 6 ways are a thing for electromagnetism. But it's not the case for SU3. Well, I promised you earlier that the shape of our failure would be the key to our success. And in order to make that happen, we have to reflect very carefully on the shape of our failure. That is, we have to take a moment to understand, what is this yellow term? Why is it so tricky? Why does it work for electromagnetism and it doesn't work for SU3? So let's take a moment to really dive into that and see exactly how everything cancels for electromagnetism, and see if that can give us a clue for what's going wrong with SU3. Okay, so having tried the 6 ways, we found something that almost works but has a bunch of other stuff that doesn't work. Now I told you that if this were electromagnetism, that yellow stuff would go away. So let's go ahead and demonstrate that. Well, in electromagnetism, U is a U1 element, e to the I theta, U dagger is just e to the negative I theta, and our gauge field is the electromagnetic 4 potential with real valued components. So right from the start, if you look at that expression with the big U dagger sandwich, you can go ahead and pull that U dagger all the way to the left side and annihilate it with U, because U times U dagger is just e to the I theta times e to the negative I theta, which equals 1. So those slices of bread simply vanish from existence. All right, well, let's go ahead and rewrite everything like so, and investigate how everything cancels out. Well, if we color code it, and first go ahead and look at the orange term shown here, when you evaluate these derivatives, you end up with the expression shown here, because theta is a function of spacetime. And so when you take the derivative of e to the I theta, you're going to end up with I times the derivative of theta times e to the I theta. And the same applies to e to the negative I theta, but with an extra minus sign. And when you examine this expression, and you realize that because everything commutes here, you can go ahead and switch things around and get everything to line up just nice and cancel out, and there's no problems, you find that that is all going to equal 0. And next, if we turn our attention to the blue term, as well as the underlined e to the negative I theta and e to the I theta, you can recognize in that a reverse product rule, and you can go ahead and compile that into the expression shown here. And then if you examine that expression, you'll find that you have a derivative of e to the negative I theta times e to the I theta, and so that's just going to be the derivative of 1, which is 0. So those blue terms also conveniently vanish into thin air. Now if you look at the purple terms, you find it's actually the same thing as the blue terms, but with some indices switched around. Once again, it's a reverse product rule. And once again, you end up taking the derivative of 1, which is 0. And so the purple term goes away and everything goes away. And so the lesson to be drawn from all of this is that when we're dealing with U1 and things commute, then everything in that yellow expression actually does cancel out. Because you can move things around and then it's no problem. But it's not the case when you're dealing with SU3, because things generally don't commute. U doesn't commute, G mu doesn't commute. And, like for example, if you look at something as simple as G mu times G nu minus G nu times G mu, that doesn't even equal 0 in general, Wait a minute. G mu times G nu minus G nu times G mu generally doesn't equal 0, because the spacetime components of the gauge field live in SU3, and SU3 matrices generally don't commute. But, hold on. G mu times G nu minus G nu times G mu generally doesn't equal 0. Oh my gosh. Do you see it? We just got 6 more ways. Okay, but hold on now. what do we really mean by the 6 more ways, right? I mean, this is not super precise terminology. This is kind of vague. So let's think about it for a moment and figure out what we're dealing with here. Okay, so going back to this analogy where the gauge transformation rule is like a lock, and we're trying to find a very specific definition of our field strength tensor that's going to let us pick the lock by finding a field that simply goes into a UU dagger sandwich from one gauge to another. Now, we tried to open this lock with our classic set of lock picks, the 6 ways, partial mu g mu minus partial nu g mu, and we failed. We found that we ended up with a whole mess of things that didn't cancel out because our matrix field U, which is comprised of SU3 matrices, those don't commute, and also the components of our gauge field, which live in SU3, those also don't commute. And so we were like, oh no, this isn't working. But then reflecting on that for a while, we stumbled into what appears to be a new set of lockpicks, which we're kind of jokingly calling the 6 more ways, okay? And don't worry, we're going to articulate this better in a moment. But anyway, what this expression is something that sure looks like it might be the kind of thing where the mess created by both of these components hopefully will cancel itself out under a gauge transformation, or at least will be something that we can combine with the classic 6 ways to come up with an entity whose components all collectively cancel out. Now, I can't logically justify why it is that one should notice this pattern and then follow this line of reasoning. Sometimes when you're doing math and when you're doing physics, you kind of go by instinct, and you see something that stands out as an interesting pattern, and you think to yourself, hey, I bet we can do something with this. It's sort of like solving a Sudoku, sometimes you go out on a limb. And we're kind of doing that here too, where you have this epiphany when you realize that a term like g nu minus g mu, in a non-Abelian gauge theory, that actually can be something. That can be non-zero. Right? Like for electromagnetism, the components of the photon field are real numbers. They live in the Lie algebra of U1, and so they always commute. So an expression of the form a mu a nu minus a nu a mu is always zero and boring and lifeless, and there's nothing we can do with it. But now that the components of our gauge field live in SU3, and in general they don't commute, it's like, okay, this is another tool that we can use. And now all we have to do is figure out how to use it. Okay, so how do we use the 6 more ways? Well, remember, we know how our gauge field has to transform from one gauge to another, right? It goes in the UU dagger sandwich, and then it picks up a derivative term. And we're hoping that under any gauge transformation, our field strength tensor, F mu nu, is going to simply undergo an adjoint transformation, properly reorienting itself in color space, but otherwise not changing. Now let's recall the mess that we found earlier, the shape of our failure, when we tried the 6 ways, that F mu nu in the new gauge is indeed F mu nu in a UU dagger sandwich, but also then it's plus all this other mess, and that's no good. So, if there's any hope of using the 6 more ways to cancel out all that mess, then we're going to have to cancel out both the top orange line and the bottom blue line. And you notice that the top orange line, it has our matrix field U, it has derivatives of U, but it also has our components of the gauge field G mu and G nu. And then on the bottom line, we have only derivatives of our matrix field U. And we also notice that on the bottom line, we have the coupling constant G in the denominator. And that gives us a clue of how we might use the 6 more ways. Now, the solution to this problem is by no means obvious. It's the kind of thing where if you're sitting down with pencil and paper, it might take you a few minutes to kind of figure this out. But in order to appropriately pace this video, I'm just going to go ahead and proceed with the solution. But please don't take this pacing as an indication that the solution should be obvious. But anyway, in the interest of time, we're just going to walk through the solution, okay? So, reflecting on the situation, let's pay particular attention to the derivative term in our gauge transformation rule. That is I over G, partial mu of U, U dagger. Now, if we look at the 6 more ways, we have the product G mu and G nu, minus G nu times G mu. But imagine this, under a gauge transformation in the new gauge, you're going to have a product of G mu prime and G nu prime. And each one of those transformed gauge fields is going to have a term I over G partial mu U, U dagger. And as part of the multiplication, when you FOIL out those expressions, that term is going to multiply with its counterpart, and you're going to end up with a derivative term involving a factor of -1/g². And because of the non-commuting nature of SU3 matrices, those terms are not going to magically cancel themselves out. So all that's to say, if we were to simply add our 6 more ways onto our 6 ways, that would not cancel out the mess, because you're going to have some non-zero terms with a factor of 1/g². And there's nothing in our orange and blue mess for those to cancel out with. You see what I mean? So what that prompts us to do is to slap a factor of ig onto the 6 more ways. Because if we slap on a factor of ig, then we're not going to end up with a term with a -1/g² factor on it. Instead, that term would simply have a g to the first power in the denominator. And that could potentially cancel out with the blue part of our mess. So you see what I mean earlier when I was talking about how this kind of math, it usually takes a while and you kind of explore different avenues as you go to the solution. So if the solution method seems kind of contrived and you're thinking like, okay, how do you know exactly to do this and to do that? The answer is that it is kind of like solving a puzzle or like doing a Sudoku, where at each step you have a few different directions you can go in. And what I'm showing in this video is kind of like, it's sort of like we're going through a maze. So we're sort of feeling our way around in the space of math and logic and reason. Of course, at the end of the day, we are going to check all of our work. We're going to make sure that our reasoning is coherent and is correct. But we are kind of going out on a limb as we feel our way towards the solution. And actually, on that topic, it is true that dimensional analysis forces us to slap a factor of ig onto the 6 more ways. However, you can also say, well, wait a minute, why not slap a factor of -ig? Because dimensionally, that should be the same, right? Because you'd end up with the same kind of I/g factor on the derivative terms. And so a priori, we don't necessarily know ahead of time whether it should be a plus ig that we multiply or a negative ig that we multiply onto the 6 more ways. And that is true. But the thing is, in math and physics, if you ever have 2 options and you're not sure which to do, just try them both and see what works, right? That's what I did when making this video, and I realized, okay, plus ig is the one that works. Anyway, so it is actually a factor of positive I/g, as we're about to demonstrate. All right, so we think we know what the field strength tensor should be. We're thinking it's going to be the 6 ways plus ig times the 6 more ways. So let's give it a try. Now, the 6 more ways, we could write that in commutator format, but there's no need. We'll let it breathe for now. It's more transparent that way. And of course, what we have to prove is that given the gauge field's gauge transformation rule, we want to demonstrate that the field strength tensor undergoes an adjoint transformation, but is otherwise completely unaffected by hopping from one gauge to another. Okay, so all we have to do is figure out, given our proposed definition of the field strength tensor, how is that going to transform when we hop from one gauge into another? So to do that, all we have to do is replace all the g's with g prime. So for example, if we look at this first term, we have partial mu g nu, and we can go ahead and write that out as partial mu acting on g nu prime, which given the gauge field's transformation rule, is the expression shown here. And next up, let's go ahead and look at this blue term, ig g mu g nu, and write that out as ig g mu prime g nu prime, where once again, the g prime is given by the gauge transformation rule. Now then, if we look at these orange terms, we recognize that they're the same as the purple and blue terms, but with the minus sign and with the mu and the nu switched around. So rather than writing all that out, what we can do is we'll just write this. We'll write minus the mu switched around with nu. So that way we can keep track of those terms without writing a whole messy bunch of terms, We'll just bear in mind that what we've written here is going to be subtracted by the same thing with the spacetime indices switched. Now then, let's begin the process of unpacking all of these derivatives. First up, if we take partial mu of u g nu u dagger, we end up doing the product rule to a product of 3 matrices, and just like we saw before, we get the expression shown here, where we distribute that derivative across the first, second, and third matrix respectively. And that's exactly the same thing as before. when we tried the 6 ways. And likewise, we have also the same thing we saw before with the 6 ways. We're going to do a product rule on the product of 2 matrices, partial nu u and u dagger, and we get the expression shown here. So that's all the same as before. There's nothing new there that we haven't seen already. But now we have this new term that we didn't have to deal with before, which is the product of these g primes. So to evaluate these, the first thing we're going to do is just FOIL them out, just multiply everything and see what we get. So I'll color code it so you can see which terms go where and how we ended up with the expression that we end up with. I know it looks like quite a mess, but it's nothing other than basic algebra. And of course, let's not forget to bring along the minus mu switched around with nu. So everything shown here, this whole algebraic mess, the true expression has a copy of that with a minus sign and the spacetime indices switched. Aren't you glad we're not writing it out in full? Alright, now because we have such a messy situation, the question comes up, does anything cancel? Well, if you look at it, you see, yeah, we can cancel a couple of things. So first up, if you look at the 2 orange expressions highlighted here, and you factor in that the plus ig times I over g is going to give you a -1, then you see that these 2 terms cancel out to 0. So that's nice. And bear in mind that the same cancellation we've just done also happens implicitly in the half of the equation that we're not writing. There are going to be 2 terms that are identical, except for the minus sign and the switching of the spacetime indices, and those are both going to cancel out. Alright, so now the question comes up, is there anything else that we can cancel out? Because it's still quite a messy situation, so it'd be great if things canceled. Well, if you look at it, it's like, I don't know if there's anything that's going to cancel. But then, look closely at this orange term. You have partial mu acting on u times u dagger. But remembering the fact that the equation shown here is actually copied and pasted with the minus sign and with the mu and the nu switched around, we realize that implicitly, in the unwritten half of the equation, there's going to be a term that will exactly cancel out this second derivative term. You see, because our matrix field U is smooth, continuous, and differentiable, and so the order that we take a second derivative, whether we do partial nu, or partial mu, it doesn't matter. And so this orange term shown here is actually going to cancel out with its counterpart in the other half of the equation. And so that term goes away. Alright, so we're starting to make some progress. Next up, what we'll go ahead and do is identify f mu nu in a u dagger sandwich. See, because check it out, if you look at these green terms, we've got partial mu g nu in a u dagger sandwich, we've got ig times g mu in a u dagger sandwich, and then we have both of those minus the same thing with the spacetime indices switched. And when you put all those 4 terms together, you recognize them as the 4 ingredients in our proposed definition of the field strength tensor. And so it's like, okay, sweet, let's gather all those up into the f mu nu in a u dagger sandwich. And now the question becomes, is all this other stuff going to cancel out? Well, it better. Alright, well, let's see if we can demonstrate that. First thing we can do is just clean things up a little bit. So we'll go ahead and rewrite these pink terms as shown here. And here we haven't really done any moves at all. We're just writing it in a slightly cleaner way, Now likewise, if we look at the second line here, we can also write these pink terms in a cleaner way. Let's go ahead and distribute through that ig. So we end up with the minus sign on the first term and a minus I over g on the second term. Alright, so the equation is starting to clean up nicely. But don't forget, we have minus the mu switched with nu. But you know what, the equation is simple enough now that we can just go ahead and write that out explicitly. So here all we've done is we've copied and pasted everything, but we've put in a minus sign, and we've switched the spacetime indices, mu and nu. And at first glance, you're like, oh yeah, this is about to cancel, because we have all these similar terms, and surely if you add everything up, everything's going to cancel out, and that'll be amazing, and we'll be done. Unfortunately, you find that in general, these expressions actually don't cancel out directly, as the color coding might seem to suggest. And so it's like, oh no, have we come all this way only for it not to work? Just like the 6 ways didn't work? Is this just another failed attempt? Are we wasting our time? Well, maybe not. what if all this mess actually does cancel out, but in a more subtle way? Can we find any pattern here that might let us be able to demonstrate that indeed all of this does equal 0? Well, suppose we color code things like so. If you look at the colored terms here, we can pull a factor of u out to the left side of all these terms. And then we can gather up the terms that are multiplied on the left by g nu, so that's all those purple terms. And we can also gather up all the terms that are multiplied by g mu, so that's all those blue terms. And now if you look at the purple and blue terms, you find that they have exactly the same form, just with different spacetime indices. But in both cases, what you have is the derivative of u dagger plus u dagger times the same spacetime derivative of u times u dagger. So I really hope that cancels out to 0, because if it does, then both of these terms, both the purple and the blue, would cancel out to 0. Okay, but what about all these other terms? Well, if we color code them like so, we can pull out a factor of I over g to the left, and then we can group them by the terms that are multiplied by partial nu u, so that's those purple terms, and also the terms that are multiplied by partial mu of u, so that's those blue terms. And what do you know? Once again, we have exactly the same expression. So all of these terms would cancel out to 0 if only the derivative of u dagger plus u dagger times the derivative of u times u dagger happens to always cancel out to 0 for an SU3 matrix U. So let's really hope that's the case. But you know what? In math and physics, it's not about hope. It's about figuring it out. So what can we deduce about a term that has this kind of structure? Well, it looks almost like what you'd expect if you applied the product rule to the derivative of u dagger u, because that would be the derivative of u dagger times u plus u dagger times the derivative of u. And that's almost a pattern match. So you're like, okay, maybe we can almost do a reverse product rule here somehow. But it doesn't quite fit, not exactly. But that's a very interesting thread to pull on, because we know that U is an SU3 matrix, and so U dagger U is the identity. And so the derivative of U dagger U is the derivative of the identity, which is constant, and so that equals 0. And so we know that that product rule expression, partial mu U dagger U plus U dagger partial mu U, is always going to be equal to 0. And so if only there's some kind of way to massage our expression into that expression, we could demonstrate that it does actually equal 0. Now, you know, in math, anything that's not forbidden is allowed. So nobody can stop us from taking that orange equation and multiplying on the right by U dagger. Right? I mean, that's a totally legit move. We're allowed to do it. We're not breaking any rules. And so now we know that this orange and green expression has to equal 0. But then it's like, hold on now, wait a minute. We know that U is an SU3 matrix, and so U dagger equals the identity. So that term drops out of the equation, leaving behind the most delightful fact that indeed our purple expression does always equal 0. Now we've demonstrated that. And so all of these terms are going to cancel out, because we've demonstrated this for the mu spacetime index, so those terms go away. But the same reasoning applies to the nu spacetime index, right? It doesn't matter what the index is. It's the form of the expression, it's the structure of this expression that always makes it 0. So those all go away. And then what do we end up with? The fact that in the new gauge, the field strength tensor F mu nu is going to transform as the F mu nu in the previous gauge in a UU dagger sandwich. Woohoo! We've done it! Nice! After all this work, we have found ourselves a mathematical object that transforms in the correct way for the field strength tensor. You know, it's a lot of work, but it's worth it, because now you've seen why it has to be this way, and that it is this way. Alright, well, now that we've derived the form of the field strength tensor for quantum chromodynamics, let's go ahead and talk about what kind of a thing this is. Well, as we've seen, it's a combination of the 6 ways and IG times the 6 more ways. Here I've gone ahead and written it in commutator format, where bear in mind the commutator of two things, A and B, is just AB minus BA. So this commutator is exactly what we've been calling the 6 more ways. Now the defining transformational property of the field strength tensor is that from one gauge to another, it should undergo an adjoint transformation. where f mu nu ends up in a u dagger sandwich. And we have just demonstrated that that is in fact the case. Now there's a subtlety here, which is that the same argument we just went through, showing that indeed f mu nu undergoes the adjoint transformation, the same argument would have been true had we scaled f mu nu by some arbitrary constant. Because imagine if instead we define f mu nu as like alpha f mu nu, where alpha is some scalar. Well, then by inspection, you can see that alpha f mu nu prime is going to equal u alpha f mu nu u dagger, right? Like, so the definition of f mu nu that we've come across here is actually kind of undefined up to a scale factor. Now, in practice, that really doesn't matter, because when we're building QCD, we have the ability to define what we mean by the units of the gauge field. And so therefore, we can just say, okay, the units of f mu nu are just going to be directly defined in terms of the gauge field as shown here, with the 6 ways and the IG and the 6 more ways, because there's no need to overcomplicate it. And also notice that the coupling constant G is in there anyway. So to the extent that the derivative terms are going to contribute a different amount to the field strength as the commutator term, that's all naturally absorbed into the value of little g. Okay, but unfortunately there is still an ambiguity relating to the sign of how we define f mu nu. And in fact, different authors use different conventions. So the way we're writing it here aligns with the convention used by Griffiths, and also the convention we used in the electromagnetism video. But if you look at Quigg, equation 8.1.6, you'll find that the convention he's using actually bakes in an implicit minus sign in the definition of the field strength tensor relative to what we've written here. And that's okay. It's just a different way of formulating the definitions. It ultimately doesn't have an effect on anything physical, because as we'll see later on, f mu nu contributes to the Lagrangian in a way that a difference in minus signs isn't going to affect. But we'll get to that later. Oh, while we're here, there's something I need to point out about the connection between quantum chromodynamics and quantum electrodynamics. So in quantum chromodynamics, our gauge field G mu lives in SU3. And as we've seen, the field strength tensor has the following form. Now in electrodynamics, the 4 potential has real-valued components, and so those live in the Lie algebra of U1. Now consider this. What if we write the same form for the field strength tensor as what we've derived for QCD, including the commutator term, that is, including the 6 more ways? Well, because the components of a mu are scalars, the commutator term is always 0, so that term vanishes, leaving us with the 6 ways. So when you think about it from that point of view, it's like, whoa, the electromagnetic field strength tensor has exactly the same form as for the strong force, but the commutator term is just naturally suppressed by the fact that the components of the electromagnetic 4 potential all commute. And so once again, we find this beautiful structural similarity between QCD and QED, where QCD is like a rectangle and QED is like a square, in that you can look at QED as kind of a special case of QCD. Now bear in mind the coupling constants are also different between the strong force and electromagnetism, so they're not exactly the same, but structurally they're remarkably similar. Alright, well now the question comes up, what kind of matrix is f mu nu? Here I'm referring to a specific component of the field strength tensor. So let's say F00 or F21, right? Because the field strength tensor, you can think about it as like a 4x4 array of different matrices f mu nu. Of course, only 6 of those are independent, because the diagonal terms are all the 0 matrix, and then the off-diagonals differ from one another by a minus sign. Okay, so it's an antisymmetric tensor. But if we zoom into the components of that tensor, which themselves are 3x3 matrix valued, then what kind of matrices are those? For example, do they live in SU3? Well, for starters, we know that f mu nu does have to be a 3x3 matrix because it involves the derivatives and the commutator of the gauge field, which itself is comprised of 3x3 matrices. But to prove that f mu nu lives in SU3, we have to demonstrate that f mu nu is Hermitian and also traceless. Because we know this about G mu. We know that G mu lives in SU3, by which we mean that G mu is Hermitian and G mu is traceless. So if we look at it piece by piece, we can ask, for starters, is the derivative of g mu a Hermitian matrix? And to do that, you can say, okay, starting with the derivative of g mu, we know that equals the derivative of g mu dagger, because g mu equals g mu dagger, and the transpose conjugate can be brought outside of the derivative, so then you can see that the derivative of g mu actually does equal the transpose conjugate of the derivative of g mu. And so yes, indeed, the derivative of a Hermitian matrix is itself a Hermitian matrix. But now what about the trace of the derivative of g mu? Does that also equal 0? Well, yeah, because if you take the trace of the derivative of g mu, that's the same thing as the derivative of the trace of g mu, and we know that the trace of g mu is 0, so therefore the derivative of the trace of g mu is the derivative of 0, which is 0. So we've just confirmed that the derivative of our gauge field does live in SU3. And in our definition of the field strength tensor, we have two derivatives of the gauge field. We have partial nu g mu, and we have partial mu g nu, both of which live in SU3. And if you have two matrices that are traceless and Hermitian, you can add or subtract them, and the result is always going to be traceless and Hermitian. And so that demonstrates that the 6 ways lives in SU3. So this is really cool. Now, if only that commutator term lives in SU3 as well, then we'll have demonstrated that f mu nu lives in SU3. So let's hope that's the case. Well, let's see if the transpose conjugate of the commutator term equals itself. So if we take the transpose conjugate of the whole commutator term, first we can pull out the scalar ig, convert that to negative ig, because that's purely an imaginary scalar, so its sign is going to flip, and then we can write out the commutator in terms of g mu g nu minus g nu g mu. And now, if we evaluate the transpose conjugate of that commutator expression, what we find is that all we have to do is switch around the order of those products of matrices. The reason being that g mu and g nu are both equal to their own transpose conjugate. But the transpose conjugate of the product of two matrices, say AB dagger, is equal to B dagger A dagger. So you switch the order of the matrices when you take the transpose conjugate. If you take that expression and distribute through the minus sign, so what you end up with is basically switching back the order of those two terms. And then if you recognize that as the commutator, what you end up with is ig times the commutator of g mu g nu, which is, exactly our commutator term. So when you work through the logic of it, you see that indeed that commutator term, ig g mu g nu, is Hermitian. So that's fantastic. But now the question arises, does the commutator term have 0 trace? To see that it does, consider the identity that the trace of the product of two matrices A and B equals the trace of BA. So what that means is if you take the trace of the commutator of A and B, you end up with the trace of AB minus the trace of BA, and because the trace of AB equals the trace of BA, those things cancel out to 0. So not only is the commutator term Hermitian, but it's also traceless. Therefore, the commutator term does indeed live in SU3. And so now that we've seen that the 6 ways live in SU3, and also the commutator term lives in SU3, we can conclude that yes, the components of the field strength tensor live in SU3. Now that's a very important result, because that tells us how we can think about what kind of a thing the field strength tensor is. You know how with the gauge field, you can think of its spacetime components as being SU3 matrices, but you can also think of having like 8 gauge fields where the components are scalar valued, each one corresponding to a generator of SU3. Those are the 8 gluon fields. Well, because we've demonstrated now that f mu nu lives in SU3, we realize that if we want to, in QCD, we can think of having 8 field strength tensors, each one corresponding to a generator of SU3. All right, so we're starting to get an understanding of what kind of a thing the field strength tensor is. Okay, let's talk about the gluon field strength tensors. So this is an f mu nu with an index A that corresponds to the generators of SU3. As we saw earlier, our gauge field has components which live in SU3. And so, remembering the octopus, we can think of the gauge field in terms of 8 real-valued fields, g mu a, where a is an index that runs from 1 to 8. And the reason we can do that is because we can always write a SU3 matrix as a linear combination of the SU3 generators with real-valued coefficients. And when you think about it like that, you realize that instead of a SU3 matrix-valued 4-vector gauge field, we can imagine 8 real-valued 4-vector gauge fields, the gluon fields. But now we also know that the components of the field strength tensor, F mu nu, also live in SU3. And so therefore, by the exact same reasoning, we can think of each of the components of the field strength tensor in terms of 8 real-valued fields. So F mu nu can be written as F mu nu A times TA, where, same as before, TA are the tentacles of the octopus, that is the generators of SU3, and F mu nu A is the 8th real-valued number that goes with the 8th generator. And so it's exactly the same reasoning as before. When we saw that we could write G mu as G mu A TA, well, we can also write F mu nu as F mu nu A TA. Now I know when you see something like F mu nu A, it's like 2 subscripts and a superscript. Well, that looks confusing. But it actually makes sense. The mu and the nu are the space-time indices corresponding to the fact that the field strength tensor is a rank 2 tensor in spacetime, and the A is the index that runs from 1 to 8 and corresponds to the generators of SU3. Okay, so how should we think about F mu nu A? Well, it mostly corresponds to the gluon field G mu A. But you have to bear in mind that F mu nu A is also going to include energetic contributions from gluon-gluon interactions, because as we saw earlier, those naturally arise from the commutator term in the definition of F mu nu. Remember the 6 more ways. And so F mu nu A is going to mostly correspond to the energy contained in G mu A, but it'll also include the energy from the interactions of the 8th gluon field with the other gluon fields. And we'll see precisely how in just a moment. Now, something I'd like to point out here is that those gluon-gluon interactions are not put in by hand. It's not something we're just arbitrarily choosing to add to the model. But no, they're an inevitable consequence of SU3's non-Abelian nature. Remember, we saw that when we were deriving F mu nu, and we saw that the 6 ways failed. We had to bring in the commutator in order to make it work, and that commutator is the source of the gluon-gluon interactions. So a non-Abelian gauge theory is necessarily going to have a gauge field that interacts with itself. Okay, but the question comes up. If the SU3 matrix-valued F mu nu is calculated from the SU3 matrix-valued gauge field as the 6 ways plus a commutator term, then how can we write the real scalar-valued F mu nu A in terms of the real-valued gluon fields G mu A? Well, let's do a little math and we can figure it out. Okay, so what do we know? Well, we know how the SU3 matrix-valued F mu nu is defined in terms of the SU3 matrix-valued gauge field G mu. We also know that because the components of the gauge field and the field strength tensor both live in SU3, you can trade in each SU3 matrix-valued object for 8 real-valued scalars. And so the question now becomes, how do we calculate the scalar-valued F mu nu A? Well, first, let's take the definition of the SU3 matrix-valued F mu nu and substitute into the SU3 matrix-valued gauge field the sum over the gluon fields, each one times a SU3 generator. See, all we're doing here is writing the matrix gauge field as the sum over the 8 real-valued gauge fields. Now, when we do this, we have to be a little bit careful with the indices of the sum. So for the first part of the definition of F mu nu, that is the 6 ways, we can just sum over the index A. But when it comes to the commutator term, we have to use a fresh set of indices for both of those gluon fields. The reason being, when you take the 6 ways of the SU3 matrix-valued gauge field, you can calculate that one at a time. So you can take both derivatives in the 6 ways and just add up the expression for A equals 1, A equals 2, A equals 8. So that's why it's okay to use the A index for the 6 ways. But when you calculate the commutator term between a matrix field G mu and another matrix field G nu, you want to make sure to express those gauge fields as an independent sum over the generators, so that we're not accidentally locking together the layers of the 6 ways calculation with the layers of the commutator calculation. So we have to keep those sums independent, otherwise we're going to be tangling up our scalar fields in a way that we shouldn't. And one way to think about what this equation means is that when you consider the 6 ways, that's kind of the way in which the gauge field is flopping around, and that's just a sum over all the ways that the scalar valued gauge fields are flopping around. But for the commutator term, there's actually going to be 64 terms inside that commutator expression, because you have to think about how each of the 8 components of g mu are going to interact with each of the 8 scalar components of g mu. So let's go ahead and simplify this equation. Well, on the 6 ways, we can go ahead and pull out the generator TA to the right side of that expression. And then on the commutator term, we can actually go ahead and pull the scalar valued gauge fields outside the commutator, because g mu b and g mu c are just scalars. So when we think about the structure of that commutator term, it really all comes down to the commutator of tb and tc. And then g mu b and g mu c are just a scale factor. And so we'll end up getting a rich landscape of interactions between the various real-valued scalar components of our gauge fields. One thing you realize when you think about this commutator expression is, wow, this is complicated and confusing. But remember, in part 2 of this video series, we saw how to get out of a commutator of 2 generators of SU3. Remember the structure constants? We can write the commutator of TB and TC as a sum over the generators TA. Now remember, FABC, these are real numbers, and the reason this formula works is because TB and TC, being generators of SU3, are both traceless Hermitian matrices, and so their commutator, as we saw in part 2, is going to be a traceless anti-Hermitian matrix. Therefore, if you divide it by I, you make it a traceless Hermitian matrix, and therefore you can pull it into SU3, and therefore, thanks to the octopus, you can write it as a sum over the generators of SU3, TA. Now, the very astute observer will remember that in part 2, we defined this equation a little bit differently. There, we said that the commutator of TA and TB is equal to I FABC summing over TC. So in other words, we switched the indices around a little bit relative to what we have here. And you might think, oh no, we got our indices mixed up. Because relative to what we wrote before, here we should actually put FBCA in order to have the indices being consistent. But, what's really nice is that because of the anti-symmetry of the structure constants, whenever you switch 2 indices around, you just pick up a minus sign. And so it's true that here we should have written FBCA. But FBCA equals negative FBAC, switch the A and the C, and negative FBAC equals negative FABC, because you switch the B and the A. And negative FABC equals FABC. And so actually, the equation we've written here for the structure constants is totally consistent with the definition we used earlier. And now a beautiful thing happens, because we can replace that commutator of TB and TC with the sum over TA, and then we can factor out a TA from everything to get the expression shown here. So isn't that neat? Isn't that really cool? Now here's where a magical thing happens. Notice that the only generator remaining in our equation is TA. See, because what we have here on the left side, we have our SU3 matrix-valued field strength tensor, and on the right side of the equation, we have a sum over the generators indexed by A. And if you look at the whole expression inside the parentheses, that's just a scalar, because you have the derivatives of the components of the scalar-valued gluon fields, as well as the coupling constant G, which is a real number, as well as the SU3 structure constants FABC, which is a real number. And so right from this equation, we can directly read that the 8th real-valued field strength tensor, F mu nu A, is going to be the expression inside the parentheses. That is, F mu nu A equals partial mu G mu A minus partial nu G mu A minus G FABC G mu B G mu C. Okay, so what do we have here? What is this equation? Well, what we have is that for each of the 8 gluon field indices, we end up with a real-valued field strength tensor, F mu nu A, which is a 4x4 real-valued tensor, very much like the electromagnetic field strength tensor. And don't just take my word for it, you can find this equation in Quigg 8.1.12. Now remember, Quigg uses a different sign convention, so just slap a negative sign onto his equation. But it's all the same, there's an ambiguity in how we want to define the sign of the field strength tensor when we're developing QCD. Okay, so let's unpack this equation. Well, if you look at the first part and compare it to the electromagnetic field strength tensor, F mu nu, which is partial mu A nu minus partial nu A mu, which at this point you're probably tired of me describing as the 6 ways, the 6 independent degrees of freedom in that expression for electromagnetism comprise the 3 degrees of freedom of the electric field, as well as the 3 degrees of freedom of the magnetic field. So in electromagnetism, the electric and magnetic fields are right there in the field strength tensor. That's what the field strength tensor is. And here we find the same thing, but we find 8 copies of it, 1 for each value of A, that is, 1 for each generator of SU3. So sometimes when you hear people talk about QCD, they'll tell you that the gluon fields are kind of like 8 copies of the photon field. And now you can see why it is that people say that. Because if you just think in terms of the 8th gluon field, and if you take the 6 ways of that field, that is one of the main things that contributes to the 8th real-valued field strength tensor. But, of course, in QCD, we also have this interaction term in our field strength tensor. Now, we can tell that this is an interaction between gluon fields because you can see that we have components of the different gluon fields directly multiplied together. And that means that one of the things that contributes to the field strength tensor in QCD is the amount of each gluon field that we have. But notice also that this product is weighted by the structure constants of SU3. And so the non-Abelian nature of SU3 and SU3 is what determines the way in which the gluon fields interact. And we'll take a closer look at that in the next video when we explore the Lagrangian of quantum chromodynamics. And so to sum everything up as far as the gluon fields and the gluon field strength tensors, you can think of each of the 8 real-valued gluon fields as being sort of like 8 copies of the photon field. But then you can think about the 8 real-valued field strength tensors as being sort of like 8 copies of the electric and magnetic fields, but rather than just being this 6 ways expression that sets 2 derivatives against each other, the strength of the field is also going to depend on the amplitude of the various different gluon fields in a really interesting way. And notice, this is a subtle but essential point, that because the field strength tensor is influenced not just by the derivatives of our gauge field, but by the magnitude of our gauge field, that means that gluons themselves carry color charge. They can act as sources and sinks of the color electric and color magnetic fields in ways that give rise to all kinds of really intricate, really complicated behavior. Okay, well, in this part of the video, I told you we'd derive the field strength tensor, and we've gone ahead and done that. So I think this is going to be a good place to end the video for today. In the next video, we're going to put together the whole Lagrangian of quantum chromodynamics, and we're going to see a few examples of how that Lagrangian can help us make sense of the strong nuclear force as it manifests in nature. Thank you so much for watching, and I'll see you in the next one. I want to say thank you to everyone who has signed up on Patreon. Your support is what makes it possible to invest the time and energy to make these videos. You're helping to make these videos a reality, so thank you so much.